Okay, everyone. So this afternoon we're going to talk about first presentations about stress drop, what has been observed and what we know from other stable continental regions. And we'll have 4 speakers. So Gail is going to present her slides first. Then Bob Dara is going to come for a couple slides, kind of revisiting things we've discussed already. Then Anne-Marie Belte, who's doing the presentation in place in lieu of Greg Barossa, will talk about our research on the stress drop in magnitude, if I'm not mistaken. And then we have Dave Bohr, who's going to come and talk a little bit more about stress drop and the relationship with geometrical spreading. And yes, and then from this we're going to segue into this more in-depth discussion of correlations, and Norm will just bring up a few slides. I hope he has some slides to kind of discuss some of the issues we need to flush out. Okay, so I'll pass the mic along to Gail, and thank you.
All right. Hello, everybody. And just let me know if you can't hear me or if I become inaudible, if I mumble too much. What I would like to do is I quickly over lunch put together a couple of slides on some of the topics that came up this morning, which is actually handy because attenuation and stress drop are one of my points, is that they are very closely linked. And I'm sure Dave will say more on this also. But coming back to some of the attenuation issues that play directly into stress drop from this morning, the one of them is that there are, in my view, significant trade-offs between the geometric spreading and the Q model when you do attenuation studies, so that it's hard to compare just one element without comparing the other. And for example, one of the things that we talked about this morning when Jack and I were both talking a little bit is how would our attenuation models compare if you looked at the whole model, just the Q. And Jack showed some comparisons of what the Q looked like in Atkinson 2004 versus the Boatwright-Seekins 2010 model. And what I'm showing here is in relation to one of the earthquakes that Jack looked at, the Rivière-du-Loup earthquake, how the whole attenuation model compares. And so the black lines there are my 2004 model, and the red line is the Boatwright 2010 model. The left is for frequency of 1 hertz, and the right is for frequency of 10 hertz. And so, I think that's one of the points, is that you need to look at the attenuation rate or the total decay over the distance traveled rather than just the Q model for the regional distances. Another point is that if you look at ensemble models, they may differ quite a lot from models that you get either from one event or several events, or from a large number of events. And I think that's another reason why my attenuation model may look different from Jack's. So for example, the 2004 attenuation model came from a simultaneous regression study that determined both source and path from about 100 events. And Jack's model used 3 well-recorded events. And so we shouldn't necessarily expect them to agree. And in particular, what I have found looking back at my 2004 model in relation to a number of recent events is that for many individual events, in fact, it doesn't agree well at all. In fact, much more poorly than I would like. And so I certainly agree with Jack that for the Rivière-du-Loup earthquake, my 2004 attenuation model does not do a good job at tying the distant observations into the source. If we want to look at, comparing apples and apples, if we wanted to say compare Qs, we might want to look just at bilinear models. Say if we wanted to say, well, how does Jack's new model compare to previous models? We could compare it with a bilinear model that came out of Atkinson and Merriu in 1992 because we looked at what the difference was that you got in Q depending on whether you chose a linear, bilinear, or trilinear model. And I'm showing on this slide the Q that we got at that time for a bilinear model compared to Jack's Q. And those models are more closely comparable, even though we didn't use exactly the same transition distances, and obviously we didn't use the same earthquakes. And you can see there that looking at that Q over the 1 to 10 hertz range, Jack's Qs would be, as he points out, somewhat lower Qs than we had got, although interestingly, the Qs that we got previously were somewhat lower in turn than Qs from another study that Benz et al. Did, which also is perhaps more comparable because it just looked at larger distances. So I guess that's point one, is when looking at attenuation, you have to be careful that you're comparing things fairly and that you're looking at really the same thing. Another point I'd like to make on the attenuation, and this will come up again in a minute on stress drop, is that if you look at any individual event or even a set of events, you can fit them with a linear model, a bilinear model, or a trilinear model. And as far as I can tell, none of these is actually clearly superior to the other in terms of fitting individual events or number of events. And this is a figure. The figure here is from Boer et al., and perhaps Dave is going to pull a similar figure up in which this point is illustrated. The 4 lines there show linear model, which is 1 over r at all distances, 2 trilinear models, the Atkinson 2004 and the Atkinson-Boer 1995, and a bilinear model from Boer and Atkinson 1992. And those 4 thin lines are all drawn to go through the data from a particular earthquake. And so you can see that, there are various models that might fit the data for an individual event. Some of those models will fit better for some events than for other events. And if you look at an ensemble, then it's a different thing again. Overall, I think that from some of the statistical tests that I've done on ensemble data sets, you do statistically get a better fit with a trilinear model, but the trilinear model appears to be dangerous in terms of it's more likely to be badly off in matching an individual event. And that's something that really I've just come to appreciate recently, is that there is a danger in the trilinear model in that because its shape is more complicated, there's a greater potential for it to be off by a large margin. A few thoughts on Norm's question, given time to reflect on it a little bit. What do we need to do with the data in order to evaluate the attenuation models? What range of models should we use to input into simulations, either point source or finite fault? And I think there's 2 approaches we can take there. In both cases, we need to, I think, look at whole attenuation models, considering both the geometric spreading and the Q. One approach is to look at well-recorded events individually. To do that, we need to have events that have data at less than 50 kilometers if we want to hope to see the whole attenuation curve, and look at it on an event-by-event basis, what attenuation model fits this event, that event, and so on. And if we can build up a library of such curves for individual events over time, then I think we can capture the variability in attenuation curves from one event to another. The other approach is to look at ensemble data in comparison to models, look at data in a given magnitude range in comparison to models. And in both cases, I think we need to try and separate out the issue of the attenuation level. I'm getting some feedback here. I don't know if you are. Oh, it's gone away. Yeah. I put together some preliminary comparisons using ensemble data comparisons in the draft report for the NGA East Path project. And I think that further work is needed in that area on how one goes about taking comparisons like that and using them to define a range of acceptable attenuation models. This is just a couple of plots from that report in which I tried to look at how the data residuals compare to specific attenuation models that are in the literature. So this is essentially taking the northeastern U.S., southeastern Canada Fourier spectra data here at 2 frequencies, 0.5 hertz and 5 hertz, and correcting all of the data for attenuation according to a given attenuation model, and doing a simple scaling correction for magnitude based, again, just straight out of the data, and then looking at the residuals. So if the attenuation model was perfect, we would expect to see the residuals all scattering about 0, and the mean residual, which is the red lines in distance bins, I've binned the residuals, we would expect that mean line, the red, to track 0 nicely. And you can see here that for my 2004 model at a half a hertz, it's not too bad at larger distances. There's a tendency for positive residuals at close distances, which means that for a half a hertz, the attenuation was even steeper than the 1.3 rate in the model. If you look at the higher frequencies, the overall trend is better at close distances, but at large distances, there's a notable trend in the high-frequency residuals that are not fitting, the data are not fitting well at larger distances at high frequencies. If we do the same thing with the data against the Boatwright and Seekins attenuation model, we get a plot that looks something like this. These residuals both look good, look better at greater than 100 kilometers, I would say. When you get into closer distances, you can see a bit of shape in the residual trends, which I think is coming out of both the fact that I think there probably is a trilinear piece there in the attenuation, and also you can see some evidence at the lower frequencies for steeper than, in particular for steeper than 1/r attenuation, which is in the model. If you look at the simplest model of all, this is the residuals compared to just a 1/r model, which dates back to 1992. And there you can see the 1/r model, again, works pretty well at larger distances. The interesting thing about the 1/r model is that it produces close to 0 residuals at near distances. And the way it does that is essentially it smooths through that transition zone, and it happens, I think, rather fortuitously for the 1/r model that you tend to get low bias at low distances and low bias again at large distances, and you just get a larger bias in the middle. And so that, I think, is a merit of the 1/r model, is that it's very simple, and it appears that overall you don't go very far wrong at close distances. So I think that we can do more comparisons of this, of data against models, and in fact use comparisons like this to try refining models and also placing, finding ways to define their uncertainty for input into the model simulation. Another area where we need to do further work is clearly on what are the differences between the ground motions and their attenuation for the northeastern data sets that I've compiled and the central U.S. data sets that Bob Herman has done a lot of work compiling. I don't yet have Bob Herman's data set. I would certainly like to play with it a little bit more. What I have had to date is a preliminary data set that was put together by Zandia and Pezesh for some work that they did, and this is just an example plot of the type of comparisons that I think can be done better with better data and more fuller data sets from the central U.S. This is an example plot that shows for 1 hertz and 10 hertz an overlay of Fourier spectra for the rock sites in the northeast compared to the central U.S. sites, which are shown in red. There's no site corrections of any sort here. Interestingly, at high frequencies, from the sparse data here, there don't appear to be huge differences in amplitude levels or attenuation. At lower frequencies, 1 hertz, the central U.S. data are notably higher, which is probably what we would expect from site effects, but clearly I think we need to do more work in this area. So that was my prelude on the attenuation issues that came up this morning, and I think they actually feed in quite nicely to stress drop issues, because the first point that I wanted to make about stress drop was that because of trade-offs between source and path, we can't really separate stress drop from path effects and attenuation. And so I don't think we should actually be trying to look at those separately, and I think that the path working group should really be the source and path working group, and I would recommend adding that scope, in fact, to the path working group. The near source attenuation rate, in particular that geometric spreading rate in the first 70 kilometers, will be critical to determining and interpreting the stress drop values. The stress drop will also trade off against kappa, although that's more of an issue, I think, in the central U.S. than it is in the northeast, because for very hard rock sites, the kappa is sufficiently low that the trade-off is not as big an issue there. And I don't really deal with that trade-off in this presentation. To look at the source and path trade-off that I mentioned, I'm pulling back up the same figure that I used a few slides ago, but this time to make a different point. This shows those same 4 attenuation models fit through the Mont-Laurier data, and what I want to draw your attention to this time looking at the slide is how different those 4 models are in terms of what they would imply for the source parameters for this earthquake. You can see that those 4 attenuation models might all be argued to fit the data to some extent or another, but if we draw them back to the source, where because we fit through the data, we have essentially ended up pegging our source estimate at large distances, because that's where the data is. And so we could use any one of these attenuation models to infer what the source parameter is, but if we were looking what that meant in terms of, say, stress drop, we would get a very different answer from each of those 4 attenuation models. So for those 4 models, we get stress drop estimates anywhere from 60 bars to over 300 bars, depending on the attenuation model. So those 2 are tied. A question that one might ask is, well, that little slide that I just showed, obviously it was for an event that was sparsely recorded, and we can't tell shape out of 1 or 2 sparsely recorded events, but can't we say what shape is best if we look at more data? And this was the question that I tried to look at in that NGA path report that I sent about an hour ago. And one of the things that I did there is say, all right, if we take the larger database that we have now, now we've got more than 3,000 ground motion observations in the northeast U.S., southeastern Canada on rock sites. And if we use those, you would think that we could perhaps discern between what would appear on the face of it to be very different models. And I just compiled a sample of 6 attenuation models, and they're the ones that are listed in this slide, to try and compare against the data, just looking strictly at the shape of the attenuation compared to data trends. And this slide just shows the distribution of that eastern data set in terms of moment magnitude and hypocentral distance there. And the data become pretty good from about 20 kilometers out. They're sparse between 10 and 20 kilometers. Most of the data are from rock sites. We have both vertical and horizontal data. On the rock sites, the horizontal and the vertical data don't appear to be all that different if you look at H over V as a function of distance. If we look at what the shape is in those data, and in the interest of time, I won't try to explain in detail how I came up with the plot on the left. The dots on the plot are normalized data amplitudes. And here, this is doing something similar to what Bob Herman does in terms of pegging the observations to pass through a reference distance. Only in this case, what I've done is pegged that reference distance out at 250 kilometers because that's where most of the data are. If you look at the distribution of data, that's really where the bulk of data are, is somewhere at around 250 kilometers. And so whatever shape of model we have, it's going to pass through the data out there. So if we just take normalized data amplitudes and we plot them, those are the black dots. And if we look at the attenuation curves from different models, the 6 models that I showed in the previous slide, those are the colored lines. And I've just shifted the models up and down so that they all pass through 1 at 250 kilometers so that we can just look at the difference in shape going in from there. And the point there, again, is to look at the source, because now we're talking about the source. And here I've drawn those lines all the way back to 1 kilometer. And you can see that those attenuation models, while all predicting similar amplitudes and agreeing with the data out where the data are plentiful at a couple of hundred kilometers, will again all have very different implications for the source level. Part of the problem, I think, is that the amplitudes do tend to decay quite steeply near the source, at least in some distance range near the source. I think that was one thing that the attenuation model that I did in 2004 did capture correctly. I think there's a lot of other things my 2004 model did not capture correctly, and some that it got wrong. I don't think it does a good job of tying the near source observations to the distant observations. But I do think that it's correct that the amplitudes decay more steeply than 1/r when you're within 70 kilometers of the source. And as soon as we acknowledge, even if we don't all agree that that's true, as soon as we acknowledge that it might be true, it complicates the determination of source parameters tremendously, because that attenuation rate inside 70 kilometers is really going to influence what we think the source parameters are, and that's precisely the distance range in which our observations are the most sparse. There's another question there that this steeper than 1/r attenuation between 10 and 70 kilometers raises, and that is what happens to the attenuation shape when we get in closer than where the data are, when we get in closer than 10 kilometers. And the data can't tell us anything about what happens to the left of where the data stops. So that, the data stopping here, and we can't say anything about what happens in here. Does this curve roll over like this? Does it continue to go straight up? Obviously, it could do anything in here, and we just can't say. I think that there are some other ways that we can constrain that shape in close, such as using the moment as a constraint on the overall amplitude level. And I'll maybe return to that point briefly in a minute. So the implications of this trade-off between the source and the path is that we can't really specify the source parameters independently from the attenuation model that we've used, and we have to link the two together in modeling. So if we're going to do simulations, we have to make sure that the stress drop, or whatever the source parameter is linked to the attenuation model so that we get an internally self-consistent model that has some hope at least of passing through the observations. And because the observations are quite widely scattered, there's potentially quite a range of models that could fit them. And this is just an illustration of how potentially different models for attenuation and source might all pass through the same body of knowledge. And what I want you to compare on there, the black lines you don't really need to look at. That's the Bohr-Atkinson NGA West model after we made some adjustments to it, just shown for comparison. The curves that are attenuation or ground motion models for the east are the red and the purple curves. And so the red curve is our ABO6 ground motion prediction equation model for response spectra for magnitudes 4.5 and 5, 2 magnitude levels, compared to all of the data in that range. And the purple curve is a referenced empirical model for the same magnitude, which is kind of a model that's pinned on the NGA West equation. And those models imply really very different shape of the attenuation. The ABO6 model has that trilinear form in it from my 2004 model, and you can clearly see those red lines have that marked trilinear shape, whereas the purple lines have a more linear shape. They smooth through that transition zone entirely, and they both might be said to go through the data in some fashion, which is more or less satisfactory depending on your point of view, but they would obviously have different implications for what's going on near the source. And so the variability of the data, when you start, more data doesn't necessarily make it better, because the variability of the data is such that it does allow, I think, quite a wide range of interpretations. The second critical issue, which you'll be happy to hear is shorter than the first issue, I'm almost done, is that the stress drop that you determine, if you're going to be thinking of the source in terms of stress drop, say if you're looking at either a point source model or a finite stochastic model, is that the stress drop is dependent on the simulation methodology. And this is something that we discovered, and when I say we, I mean Ken Campbell and Dave Bohr and myself, when we started trying to figure out why we were having difficulties getting the same answers using different simulation programs. And one of the things that we discovered, and we did a little paper on this in 2009, and since done a little bit of follow-up work on that, is that if we look at 3 different stochastic simulation tools, either the stochastic finite fault model using the XSIM program with one of 2 different normalization methods that we talked about, or if you look at the stochastic point source model using SMSIM, or if you look at Frankel's hybrid broadband method, the stochastic portion of that, they all are stochastic methods at the high frequency, but none of them will predict the same high frequency ground motion over a good range of magnitude and distance for the same value of stress drop, simply because of the nature of the way they are dealing with stress drop and the way they're doing the simulation. And this is just an illustration of that point from the paper with Dave Bohr and Ken Campbell in 2009, where we looked at point source stochastic simulations using SMSIM with finite fault stochastic simulations using XSIM with 2 different ways of normalizing the high frequency amplitude, all using the same attenuation and the same source model. And you can see we predict different, or the same stress drop, and we predict different ground motion simply because of the way the models interpret what stress drop means. So I think that's another issue that we need to be careful of when we talk about source parameters, as if we're talking about stress drop, it is not only tied to the attenuation model, it's also tied to the way that stress drop is actually implemented in the simulation code. I think that the implications of these issues for determining stress drops from the data is that if we come up with a list of measured stress drops, they're only really meaningful within the context in which they were derived. And if we're looking at ground motion prediction equations, I think maybe the 2 most meaningful measures might either be the stress drop from the high frequency level of the Fourier spectrum, And that's relevant if you're using a Bruin model for a point source stochastic simulation. If we're doing that, I think that a good idea is to constrain that we need to find some way to constrain the near source attenuation or the near source amplitudes so that we match the moment end of the spectrum. That's one of the things that we found from some of the comparative studies, is that it doesn't really make much sense to talk about what the Bruin stress drop is in terms of the high frequency level if the corresponding low frequency level doesn't match the stated seismic moment for that event. So that's one way of looking at stress drop, is from the high frequency level of the Fourier spectrum. The other way is to simply look at it as a calibration parameter that's input to a simulation model and used to match model predictions to data. I think that's perfectly fine. Also, we need to bear in mind that stress drop is of course model specific. A final point on the stress drop is that there's lots of other different ways that have been used to measure stress drop. If you look in the literature, there's many measurements of stress drop: apparent stress, static stress, and so on. And I think that all of those are potentially useful as relative measurements between different regions, but the absolute values of those parameters may not be directly applicable as input parameters to ground motion prediction equation development because of this problem that the stress drop measurement is only meaningful within the context in which it was derived. So in terms of getting on to data, what we actually know about stress drops in light of the previous remarks regarding context, I've tried to sort of take a minimalist approach to that, looking at only what is known within sort of very specific model context. And if we look at Fourier data, this is a slide from a recent paper in SRL, in which myself and my colleague Karin Asatorians looked at the Val des Bois earthquake and the Rivière du Loup earthquake and a number of other magnitude 4.5 to 5 events that have known seismic moments, so that we can use the moment as a constraint on the low frequency end of the Fourier spectrum, and then essentially we're using the data and its attenuation to look at the shape of that spectrum and what it implies for the high frequency level relative to the known seismic moment. And for comparisons of that nature for earthquakes that we looked at that are relatively well recorded and have a known moment, stress drops that we find are in the range from about 150 bars to 300 bars. That again is a apparent source spectrum from the Fourier data, which might be something that you would use, for example, in an SM-SIM stochastic point source simulation. Another way to look at it is what is the stress drop via calibration to some simulation model. And maybe just to make a couple of comments on that. The previous ground motion prediction equations that Dave and I did in 1995, I think that we showed, and people have pointed out to us numerous times since then, they've said, well, your 1995 model we think matched the data better than your new model. And to a large extent that's true. So that in terms of calibrating to a simulation model, you could say that the stochastic point source model that we used in 1995 matched the data pretty well with a stress drop of 180 bars. So that's a model-specific stress drop, specific to that model. Our new model, where with the original normalization scheme, and I'm not going to go into the difference between the two normalization schemes because it gets too long and involved, but with our original normalization of amplitude schemes scheme that we used in 2006, you could say that the data around magnitude 5 matches with a stress drop level in that model of about 250 bars. And we have recently written a paper which is in review in the bulletin, in which we've proposed some adjustments to both the NGA West 2008 model and the AB06 Eastern model to align them better with moderate magnitude data. And this slide just shows a comparison of those two revised ground motion prediction models at low frequencies, or low periods rather, and high periods. So again, that's just an example of using stress drop as essentially a calibration parameter for a specific simulation model. So I think that in the context of this project, that could certainly be used with a point source simulation model, that one can essentially pick the stress drop and its uncertainty based on the constraints provided by the data within the context of that specific simulation model. A final note, we can't, I think, end this presentation without at least mentioning intensity. Intensity is the forgotten ground motion parameter, even though we do have a significant body of information on intensity of ground motion from past earthquakes. And one might argue that all of the most important earthquakes in the East, intensity is the primary data source for those earthquakes. Studies on looking at the differences in intensity between the East and the West. This comes from a paper that I did with Dave Wald in 2007, where intensity data would suggest that stress drops are significantly higher in the East than they are in the West. The curves there are comparing intensities for magnitudes 4, 6, and 7.5 in the East and the West, and up to even distances that are relatively close. I think that the intensity data are fairly convincing that there is something which is causing a larger ground motion amplitude in the East than in the West, and stress drop is probably the most likely candidate there. And so if we look at a stochastic point source simulation, previous studies suggest that maybe something around the 80 bar level is about the right stress level in a stochastic point source model for the West. If that's so, we should probably be looking at a factor of anywhere from 2 to 3 greater than that to match in the East. So another way we might think about stress drop is relative to Western simulations. What are the needs in terms of looking at Fourier methods of estimating stress drop and source in the East? I think that it is probably timely to reevaluate stress drops in light of attenuation models and their complications. I think we need to rethink to what extent we can get the source spectra out of regional observations, given the complications that we know are there in the attenuation model. And I think that we need to determine stress drops using a robust procedure from the Fourier amplitudes from a few, at least from all of the well-recorded events in the new database that's gathered, and particularly focusing on events where we have distant observations as well as observations in close to the source. Simulation methods, we can do the same thing. With any simulation method that's being used in ground motion prediction equation, we can determine the stress drop that applies within the context of that model for well-recorded events. The point source is the most transparent, but we can also do the same thing with finite fault models, but I think that's specific to every single model. And I think that the stress drop values need to be tied to the ground motion prediction equation development, in that there might be a different set of stress drop values and uncertainty that apply for each attenuation model. So again, those things are linked. We could also look at modeling studies to try and come up with differential estimates of stress drop between the east and the west that would be consistent with the intensity data. So finally, the conclusions out of all that is that in terms of the range of value, I think that eastern stress drops in the context of stochastic point source simulations, depending on the details, are probably somewhere in the range of 150 to 300 bars as a mean. Variability, I think we need more work on. The simulation parameters are interrelated, especially the source and the path, and we can't really look at one separately from the other. Different simulation methods, and in particular all of their details, the small stuff, all has different implications for how those input parameters will translate into the output that we get out of the ground motion simulations. And so that I think that the ground motion prediction equations very much need to be developed as whole models in order to ensure an internally self-consistent model that ties the data to each of the model parameters and the methodology itself, and that in doing so, those models might need to draw sometimes on a wider body of knowledge than may be contained in the official database for well-recorded earthquakes. For example, some of the attenuation issues, what's happening close to the source, may only be addressed by looking at smaller earthquakes because there's so many more of them and they tend to be better recorded. Similarly, we may want to use inferences from other sources of data like intensity that are hard to, again, put into an official ground motion database. So obviously the ground motion database is a great thing, but we may need to sometimes draw from other sources in developing ground motion models. And that's it. I'm hoping the silence on the line doesn't mean that I lost the connection 5 minutes.
No, we're just not a group that applauds or reacts much, but we're all there. Everybody was listening. I think if you want to stay there, Gail, we're going to go ahead with the other speakers.
Yep.
We'll keep the discussion points to be combined at the end. Is that okay with you, Norm? Okay. So
that's
we'll do
fine.
that.
Just let me, are you going to mute my line?
Yeah. But
okay. Good. Just so I know if my line is muted, I will happily move around.
And you can have your cat over.
I'll put it back on speakerphone if it's muted.
Okay, and like we did earlier today, so Gail, if you need to talk or you want to, interject, we just sent a text like you did.
Yep, I'll just text a comment, and in fact, you don't necessarily have to put me back on. If I just text a comment, you can just.
I'll repeat it.
You can just read the comment out. That's fine.
Okay, thank you so much. We'll talk to you in a bit in the discussion.
Before I go, I know Dave is there. Dave, do you have your email running?
Are you checking your email? Yeah.
Okay. So, because I know Dave will be putting some stuff up, and Dave and I, we think alike after all these years, so I may send stuff to Dave and he can jump up too.
Okay, so yeah, he's okay with that.
Okay.
Okay, thank you. Bye.
Bye.
Okay, so I think we had Bob come back up and, oh yes, you need to take control over.
Going there a way to quickly get to the end? 3. N minus 3. Perfect. Yes. Good afternoon. I have just a short presentation. I just want to show 2 slides that address 2 of the topics in the agenda for this afternoon session, and they are, is the stress parameter magnitude dependent, or is it a constant? And 2, another slide that you've seen before on the Saguenay issue. So this should be a pretty short talk. Okay. This is a slide we showed yesterday, and it shows the estimates from about 24 earthquakes recorded in the NGA database. So all these earthquakes are well recorded. The smallest number of points that went into the inversion for these earthquakes is 10. The largest is Northridge, over 130 points. And they're basically crustal earthquakes in California. They all also have fairly well-determined finite source models. And that's the part that allows us to determine whether or not the stress parameter, whether or not we have deep slip or shallow slip. Now, you can look at this slide and see, at least in Western North America, perhaps a trend for stress parameter decreasing as magnitude increases. Now, there are not very many data points on this slide, but we took quite a bit of compare to all the strong motion data. So this data occurs basically from right on top of the source out to basically 100 or 150 kilometers. So it's definitely strong motion data recorded near the source. We see what we can what it looks like is a trend, especially if you get about magnitude 7.5, for the stress parameter to be less than it is for smaller earthquakes. One of the other results I talked about yesterday was looking at an inversion for the 4 NGA ground motion prediction equations, and we can also invert that data for stress parameter. And we did that at 3 magnitude levels and at 7 or 8 distances. And for 5.5, the average for strike slip was 66 bars, which is, oops. Well, at 5.5, it's at 66 bars. I can't seem to get the cursor to move over there. At 6.5, it's 45 bars, which plots pretty much right in the middle of those X's. And at 7.5, it's at 24 bars, which plots just a little bit above the X at magnitude 7.5. And that's just for strike slip. So you may recall from yesterday, for normal, the numbers would be slightly less. But for reverse faults, they'd be about 25 to 30% greater. So when we invert, so we have 2 types of data, even though they're both NGA data sets, that show a trend of decreasing stress parameter, in this case, with magnitude in Western North America. It's up for other committees to decide whether or not it's transferable to Central and Eastern North America. Second slide shows just if we were going to take what at this time are standard modeling parameters. So this is looking at Saguenay data. And there are 5 curves. One is the 50th percentile. The solid curve is the 50th percentile from the 2 closest Saguenay stations. Most of the data, as you know, is at quite a bit larger distances. And we just applied our normal stochastic model in the east, which currently right now has a stress parameter of 120 bars and a kappa of 0.006 seconds. And that's the CEUS single corner model. For the CEUS double corner model, that's just an application of Atkinson's 1993 model. And for that case, you just plug in magnitude 5.9 and out comes the 2 spectra. You can see immediately that we could do a better job if we, say, for example, high frequency added more kappa. But currently, the hard rock kappa we typically use is 0.006 seconds. Both these records, the peak in the spectra is at lower frequencies, suggesting a higher kappa. So we can, if we want to match these better, we can do that. But this is just an example of what kind of the standard simulation does without adjusting the parameters for a specific set of earthquakes and data. And it basically shows that the double corner model of Atkinson, which is shown by the dashes and crosses, is closer to the data, especially at longer periods. And that's one of the attributes of the double corner model, and one of the reasons Gail initially developed the model. At high frequencies, they're both relatively the same, and with a crossover of near 1 hertz. Well, no, in this case about 5 hertz. And again, for these two close-in data sets, we see that both models tend to overpredict the data at longer periods. All right, but in both cases, we could, if we monkeyed with the parameters of the model, I know for our model we could do better by adjusting kappa. So those are the 2 points I wanted to raise that were in the agenda, and that's all I have to say. Thank you very much. If there's questions.
Okay, we're going to have Anne-Marie Balté come over and talk about stress drops and scaled energy.
All right, so I'm Anne-Marie Balté. I'm a PhD student with Greg Baroza at Stanford. So I think this ties in nicely to what Gail was mentioning, and I'll go through our method that we use to determine stress drop and scaled energy. So just a little introduction reminder. Radiated seismic energy, there we go, has the integrated overall source frequencies here of the source spectra. And so in our method, we really we try to recover actual source spectra by removing the path effects. And you can take a look called scaled energy, all right, and which is just the ratio of the radiated energy to moment. And the apparent stress is simply mu, or the modulus times that ratio. So is it? There we go. Sorry about that. So in our method, we use a small co-located event, usually an aftershock to a main shock, as an empirical Green's function. And doing that, we can remove the path and site effects. So over here, you have all these co-located events with similar path effects there. And what's recorded, obviously, is some combination of source, path, and site. So then taking like the stress drop, we're using a Bruin type model for a circular crack. And we'll model the corner frequency and the moment, and we can put that in using a shear velocity to find a stress drop here. And then we can also compare the stress drop to the apparent stress. And this is a theoretical, using the equations above, combining them, you get a relationship of 4.3. Okay, so just some past studies. On the top is a compilation. On the y-axis, you're looking at the scaled energy across many orders of moment, and you can see it's generally pretty constant, and the average ratio is about 1 megapascal of apparent stress, so 10 bars. And the bottom figure is showing some results from Kevin Maeda, and we're looking now at the radiated energy along the left axis. So he's finding that it's increasing, the ratio of scaled energy to moment is increasing as you go to higher moments. So these are pretty contradictory results. And then looking at stress drop, on both these figures, the diagonal lines are lines of constant stress drop, and we're looking at the corner frequency along the x compared to the moment. Sorry, I said that right, the corner frequency is on the y-axis. So on the left, a compilation of a bunch of studies from Allman and Scherer is that there's really no increase in the stress drop, or decrease really, with moment. But on the right here, you're seeing there is an increase of stress drop with the higher moments. Okay, so I'll take you through the work that we've done. And we have 4 data sets in Japan and 4 in the western U.S. So we don't have any work directly in the eastern U.S., but hopefully we can make some relations that'll make this make a little bit of sense there. And so in each case, we have a co-located main shock, aftershock sequence, or a swarm. So we have the Niigata 2004 and 2007 earthquakes, the Iwate Miyagi, which is infamous for its 4 Gs of acceleration, and an offshore sequence, Kameishi. It's a repeating sequence with a main shock magnitude of about 4.7. And that one is a bit deeper, and it's on the plate interface, whereas the other three Japanese sequences are shallow, sort of crustal earthquakes that might be considered intraplate. And then in the U.S., we have a sequence from Wells, Nevada, magnitude 6, 2008, which is really well recorded by the U.S. Array. And then the Parkfield, 2004, Hector Mine, 1999, and a swarm just south of the U.S. border with a few magnitude 5s. So in each case, we have a pretty good station distribution and nearly co-located events, which is important for our empirical Green's function method. Okay, so briefly, we use a CODA methodology as well as an empirical Green's function methodology here. So we use the CODA because it's more stable than direct wave measurements, and we don't have to be as particular with the empirical Green's function selection. So we narrow bandpass displacement records, and then we use a time window in each record to become, that becomes the CODA spectral point. And then the second step is to use an empirical Green's function to remove the path effects. So the small event is modeled as an ideal Broom-like event, and we sequentially remove the path effects by deconvolving from larger events. So then we've created source spectra from which we can measure energy and apparent stress, the moment, and the corner frequency, which can go into the stress drop. So I'll step us through the methodology here. So on the top we have this broadband record, and we narrow bandpass it. I'm just showing 3 particular frequencies here. And we take a window that starts just after the S arrival and decays in time. And that's going to become, each window there is going to be averaged to become a spectral point. And the window length is set here by smaller events to avoid a bias. So on the top we have a magnitude 5, and then a magnitude 4, and a magnitude 3. These are all from the same sequence at Cerro Prieto in Mexico 2 years ago. And you can see that well, it may be difficult to see, but the records are pretty similar, and the narrow band CODA decays really similarly to each other. So we use the average over those time windows to create the spectra. So each value over the time window becomes one of the points on the right-hand part of the slide. Magnitude 5 is in blue, and the 4 is in yellow, and then the 3 is in green. And there's a lot of other events in between, so we have a pretty rich data set. So that's I call it the CODA amplitude spectra, and we're going to use the smallest event as an empirical Green's function to now remove the path effects. So we're going to use a Bruin model here to ideally model the smallest event. So it has a low frequency asymptote, that's the moment, corner frequency, and it decays as omega squared. And we're assuming that the smallest event has a short duration, so it can be modeled as an ideal point source. And then we'll use a stress drop of 3 megapascals and a shear wave velocity of 3.5 kilometers per second to model an ideal corner frequency that then goes into that spectral shape here. So it's important to note, though, that these assumptions of the shape and the ideal spectra only apply to the smallest event. So let's say the smallest event is just modeled to be that shape, and we're going to sequentially correct the larger events in the same frequency band as that event. And then we'll move up to each next larger event, and we flatten the lowest point, assuming that it's reached its low frequency asymptote. And finally, we can tie all of the events to an absolute moment using the largest event. So it's essentially, we're deconvolving the smallest event from all the other ones, but because we're in log-log frequency space, it's just a simple subtraction. So now we have a source-corrected spectra, and you can see that smallest event is the ideal empirical Green's function shape. And by just doing this correction, we recover a pretty nice Bruin spectra with an obvious corner frequency. So finally, to measure the radiated energy, we just integrate under the velocity spectra. And then to measure the corner frequency and stress drop, we just model these spectra with a Bruin model to pull out the corner frequency there. Okay, so the radiated energy is on the left, and I put lines of constant apparent stress now. And the different dots within the colors are all the measurements at the different stations. So we have between 15 and 20 stations for each data set, ranging from, in Japan, very close in the U.S. about 50 kilometers out to about 200 kilometers. And then on the right, it's the same data, but we're looking at the ratio of the scaled energy now. And we can put a fit line there. In this case, there's very little dependence, so it's 0.16, and then plus or minus 0.09, and that's showed in the pink dotted lines of the confidence on that fit. And then we can take the measurements of each event at all the different stations and turn it into a box plot. A box plot is just a really nice way of a non-parametric representation of the different data. And you can see pretty easily where the median and the percentiles lie, and any outliers that are past 1.5 times the interquartile range are shown in the pluses. So it's a quick way of seeing how tightly clustered our data is. And then one more thing to think about is the effect in our model of the stress drop on the EGF, the empirical Green's function. So if we use a stress drop of 1 megapascal, we put that into a empirical Green's function, calculate the corner frequency and the ideal balloon shape, and propagate that through. We see we have a slight scaling here of 0.88. If we use a much higher stress drop of 10 megapascals, then we get a slightly negative scaling. So if we use something right in the middle, like 3 megapascals, then we have nearly zero scaling, 0.16. So we use it in the rest of the methodology. We use stress drop of 3 megapascals for that empirical Green's function, and that's pretty consistent with a lot of other studies to use the 3 megapascals. So here we're looking at the energy on the left. Again, this is from that same Mexicali swarm, and this is just to show that there's no dependence. Once we've removed all these source effects, there's no dependence on the distance. So it's just showing the different stations and the different colors, and they're actually separated along the x-axis for clarity, but they're all looking at the same event. So you can see that each bin of distance ranges has pretty similar distribution, and the mean is pretty similar for all those. So I think that this method really it validates our empirical Green's function approach in that we're really removing all of the path effects there. Okay, so taking a look at the scaled energy for the 4 Japan sequences, you can see that in all cases there's our fits include a zero slope intercept, so there's no increase of the scaled energy with moment. And also taking a look at the box plot scatter of the data, you can see that most of the data are pretty tightly scattered, so that we're recovering pretty consistent measurements of each event across many stations. And likewise, there's the same kind of data for the U.S. sequences. And again, in all the cases except for this Hector mine, we're including the zero slope intercept in our best fit. So overall, we conclude that there's no scaling of radiated energy with moment. And you can see the orange triangles in the back are from the U.S. study, and then the Japan data set is overlaid on top. And this is on top of the Ide and Barossa figure. So then we take that source-corrected spectra and we can model it with a Brun omega squared decay and find the corner frequency. On the left we have the Parkfield spectra stacked over all of the stations. And you can see that the Brun model fits it fairly well, and we can pull out the corner frequency. So on the right-hand side we have all the corner frequencies from our 8 sequences on all of the events. And it's something like 200 events or 150 events in total that we've looked at, the main shocks and all the aftershocks. And I've added the lines of constant stress drop for 3.6 kilometers per second and 4.4 kilometers per second for beta. So in all of the sequences, we use 3.6 kilometers per second, except for the Kamaishi sequence, because it's much deeper. So we use a shear wave velocity of 4.4 kilometers per second. That's the dashed line. You can see here the trend is fairly consistent, that there's really no trend of increasing or decreasing stress drop with moment. Okay, so same data again. So now we can look at what the range of our stress drops are. So on the right, we have a histogram of our distribution, and you can notice down here we have 2 really low events, and I'll talk about this briefly in a minute. But besides those, it's a pretty nice normal distribution. So the mean of all of our events is 5.84 megapascals. And the standard deviation here that I cite is the plus or minus is just one standard deviation. And on the right, there's results from Allman and Shearer 2009 showing pretty similar results. Their means a little bit lower, 3.85 megapascals. And that's from a global compilation study of almost 1,800 events, but using pretty similar methodology. And then they went ahead and divided it up into tectonic regimes. And particularly the last two lines kind of summed up some of the other regimes, the interplate and the intraplate. And you can see in general the intraplate is almost a factor of 2 higher than the interplate. So we're going to be able to make a connection from some of our results into the eastern U.S. using this interplate-intraplate relation. And then this is a figure from Kanamori and Anderson in 1975. And again, they have this interplate and intraplate distinction. And I just highlighted a few events here that are similar to some of the events that we've looked at. So the Niigata 1964 is pretty similar to our Niigata 2004 and also the offshore Niigata 2007 that we've investigated in here. That's classified as intraplate because, again, it's a shallow crustal event. And furthermore, there's the Truckee 1966 and the Fairview Peak, Nevada 1954, which are also classified as intraplate. And that's maybe similar to our Wells, Nevada earthquake. So keeping that in mind, the left two panels are showing the overall stress drop for all of the Japan events and all of the U.S. events. And there we have a slightly higher mean in Japan of 6.6 megapascals and 5.1 megapascals in the U.S. And again, this is for our Western U.S. results. And then I've divided them up in the right panels. I took out that Kamaishi sequence, which we know is much deeper, and so we expected to have a higher stress drop. And indeed, that's true, because then the mean lowers to 5.12, and the mean of the Kamaishi is much higher, it's 18.8 megapascals. And it's about it's almost 50 kilometers depth on the plate interface. Likewise, I took out the Wells event on the Western U.S. data. You see that the Wells sequence has stress drops about 15 megapascals, while the other ones are much lower. So just pulling those two numbers from Allman and Shearer, their intraplate is about 5.95. Let me see. So we see pretty similar numbers here for these three sequences. And then their interplate is a bit lower, which is consistent with what we have here for our California strike slip earthquakes. We can also take a look at the correlation between stress drop and apparent stress. So apparent stress on the x-axis against stress drop. And our results are fairly consistent with the theoretical relationship ratio of 4.3 using all of our equations. However, again, we notice that there are these anomalously low events, and we have a few events that have pretty high apparent stress and stress drops. And we've taken a look at the waveforms there and confirmed that those are actually anomalous events in comparison with some other nearby events that they show. The low apparent stress and stress drop events have corner frequencies that are much lower for their moment, and they decay much faster beyond the corner frequency. In contrast, the high stress drop events don't decay quite as fast. They're not quite omega squared. So the spread and distribution is really real data spread, and it's not an artifact of our method. So just to wrap up, we don't see any dependence of either apparent stress or stress drop over 8 orders of magnitude of moment, but there are real variations in apparent stress and stress drop, which we try to quantify here. So deeper events, as we know, as we expect, do have higher stress drops, as in the Kamaishi sequence. And intraplate, which may be similar to Wells, Nevada, has higher stress drops, as well as the Japanese intraplate events have slightly higher stress drops than the California events. And we can pull out these anomalous energetic or enervated events. And because we're using the same method on all of these sequences, it's really valid to compare the mean there. And our results are pretty consistent with previous studies supporting constant stress drop. We don't see any dependence in the self-similar earthquake model. So what else can be done? Our current empirical Green's function CODA approach does require nearly co-located main shock aftershock swarms. So it may not be as applicable to central and eastern United States, but it's possible that it can be adapted for aftershock sequences that aren't as rich. So it's also possible to take a look at some other stable continental regions using our same methodology approach to get a comparison. And as was brought up before, the US array poses a great opportunity to do some of this work. So any significant earthquakes will be very well recorded, and it's possible to use this approach there. And there should be a great wealth of data to develop or test these relationships and take a look at stress drop. So that's all I have.
Thank you so much. It's becoming more and more apparent that we need more earthquakes soon. Okay, Dave, would you be ready to come and add to this? So we're going to segue into correlation, so don't worry too much about the time. So after you, after your... Well, we're not scheduled for a break, so we'll just, but I see the time there. Don't get distracted. Just go over what you need to.
Fine.
Thank you.
Yeah, I wasn't prepared to do this beforehand, so I just pulled some figures out of the paper. There's no nice colors or anything, so I apologize in advance. And Gail's already covered some of this material as well, but this is from a paper we did where you can see the title, Determination of Stress Parameters for 8 well-recorded earthquakes in Eastern North America. And I think you might find some of the figures interesting if I can figure out how to make this work. This is a table of the, does this show up okay? Yeah, I guess it does. This is a table of the earthquakes that we used, and you can see the names and the depths and the magnitudes and so on. And there's a lot of detail there you probably don't have to see, but you've already heard about some of these earthquakes. And as Gail was trying to emphasize that any stress parameter that you determine has to be tied into the particular model that you're using. And one of the things that I think is really important in all of the work we're doing here is that we be consistent. So it's really not correlation so much I'm talking about, it's consistency. So if you're deriving a stress parameter or geometrical spreading or Q or something from analysis of data, then if we're going to use that information in simulating ground motions that will eventually, from which we'll eventually derive ground motion prediction equations, we have to be consistent. We have to use all of the parameters that were used in deriving the information, like stress parameter or Q, in the simulations, in the forward simulations. And this just is a table from our paper that shows some of the things that we have to specify in at least my version of the stochastic method. The partition factor, average radiation pattern, these are scalar effects. And if you don't include those things, all of the results are going to be scaled by constant factors. So you can see there's a whole bunch of things here, including, I should use the cursor. Come on, cursor. Come to Daddy. Oh, here it is. Okay. Distance dependence of duration. That's something that we really haven't talked about, but it is important. And it's something that I think with the analysis of the data we're doing, we should be deriving distance dependence. This comes from analysis that Gail, whoops.
Did we use the microphone or?
Tell me where, is this okay? Can you hear me? Okay. Going back. Okay. So the duration dependence, we find that the duration, which is just the path effect, and it's sort of essentially an empirical factor that accounts for the scattering and the fact that duration usually increases with distance. This comes from analysis of fairly small earthquakes that Gail has done. And certainly we can do this as part of the, once we get the more complete data set, this is something we definitely should do. The other thing that I have at the bottom of the table here, this is really awkward, is the crustal amplification. So this is another factor that I incorporate You can see it's not a big deal. It's like a factor of 1.4. It's frequency dependent. It comes from a velocity model and using a simplified way of computing the amplification factors. In this analysis, we use 4 different geometrical spreading functions, and Gail's already talked about those. We have the Atkinson 04. In this table, again, I pulled it out of my paper, and some of the math type equations disappeared. So, but basically, the first one is a trilinear model with r to the minus 1.3 and close. And then there's the Atkinson-Bohr model, which is -1 out to 70 kilometers. It's flat out to 130. Then it goes as r to the minus 0.5 beyond that. The Bohr-Atkinson model was r to the minus 1 out to 100, and you can see that it's r to the minus 0.5 beyond that. And maybe this didn't appear on this, but there's just a 1 over r model as well, a simple model all the way out to all distances. And unfortunately, it doesn't show, but there's a Q that is associated with each one of these things. And I think we tried to make the Q compatible so that in an overall sense, for frequencies of 5 or 10 hertz, is what we're concerned with, the overall attenuation combining the geometrical spreading and the Q gave comparable decay with distance. This is a mess, but this is really the summary of everything. This shows on a given line an earthquake, and here's the moment magnitude in the next column. And then for the Atkinson, then we have 2 columns for each attenuation model. Atkinson 04, AB 95, Bohr Atkinson 92, and 1 over r. And then the subcolumns are the frequent or the periods of the response spectral amplitudes that we're fitting. And we did an inversion process. So this is not just sort of eyeballing it. We actually did a formal inversion to come up with the stress parameter that gave us the minimize the residuals. So you can see if you look at, well, first of all, if you look at the 0.2 and the 0.1 values, I'm sorry, gang, I just can't, there's no cursor. No, it just disappeared. Oh, here it is, it's back again, okay. So what we find is fairly good consistency for a given attenuation model, a given earthquake, between the 0.1 and the 0.2 second oscillator responses. But if you go across for the different attenuation models for a given earthquake, you see that you have large differences, and that's something Gail had emphasized before. So that's one of the important findings, in fact, probably the most important finding in this study, is that the stress parameter that we derive is strongly dependent on the attenuation model. This is actually kind of obscure, but it's basically showing the uncertainty, the standard deviation of the results around the best models. But basically, you have to just accept what I'm going to tell you, that all of the models fit the data equally well. That's the bottom line. And so you really can't discriminate between the various attenuation models according to how well they fit the data. What I'm going to show now, well, first of all, this is the magnitude distance plots for the data that we used, and you can see most of the data are at distances of 100, 200 kilometers. Now I'm going to show a series of figures, I hope. Nuts. No response. Is that because? All right, here we go. I got it. Okay. I'm going to show the data and the fits to the data for the 8 earthquakes. The first one is the Nahani earthquake, and because we only have 3 close-in stations, I'm not going to show the ground motions as a function of distance, which is what I will show for the other 7 earthquakes. But you can see here we have actually the ground motion as a function of period for station 1, 2, and 3, and it shows the fits we have for the 4 different geometrical spreading functions and the optimum stress parameter for each one of those. And you can see they all fit equally well. None of those models fit all of the station spectra really well, but in an overall sense, this is what you get. This is the best. Okay, now we go to a series of plots that all are going to look the same. On the upper part, we're going to have PSA at 0.2 seconds as a function of distance. And the lower part is a map showing where the earthquake is and where the data and where the stations are. And the upper plot I don't know if you can see it, but the points that have the vertical bars, kind of filled in with the vertical bars, those are vertical data converted to H. And the open circles are horizontal data. So this helps get an idea of where we have vertical data, where we have horizontal data, and the comparison between the two. The vertical data have been converted to horizontal using H over V factors that Gail has determined in previous studies. This is the Saugony earthquake, and again, the curves show. Let's see, we have 5 curves. 4 of them show the fit with the different geometrical spreading factors, and then the other one, the gray curve that's very low here, this guy, is the Atkinson-Bohr 06 prediction for that particular earthquake. Okay, so you can, as Gail was trying to emphasize, we can fit pretty well the data in an overall sense, but we don't have enough data for any one earthquake over the whole distance range to really pin down the proper attenuation. Come on. That's Saugony. This is Mont-Laurier, which is what Gail was using, showing in her analysis. I'm just going to run through these so you can get an overall sense of how well things fit. This is the Cap Rouge earthquake. Saint-Andamont. I don't speak French. I apologize, Christine. Capala? Something like that.
That's not French.
I know it's not French, okay. Possible Forks. And Riviere de Loup, which is, of the earthquakes that we're studying, this is the best recorded earthquake because we did the study before the Val de Bois earthquake. So that's the analysis we did, and the point of this figure actually is to show the sensitivity of the derived stress parameter for a given geometrical spreading function as a function of the moment magnitude of the earthquake. And the reason that we were doing this is that in AB06 we had the wrong moment magnitude for the Riviera de Loup. We used magnitude 5, and it should have been 4.67. And you can see that there's a tremendous difference in the derived stress parameter. And this is kind of an overall thing you should keep in mind as well, because when we talk about moments, we probably don't know moment magnitudes to better than 0.1 or 0.2. And so there's definitely going to be an uncertainty in the derived delta sigma associated with the uncertainty in the moment magnitudes. This is an attempt to summarize the results that we have as a function of moment magnitude using the Atkinson 04 geometrical spreading function, and it shows the values that we used in the Atkinson-Bohr 06 study, and those are the solid squares for each earthquake, and then it shows the new values that we have based on the analysis in this paper for both 5 Hertz and the 10 Hertz oscillators. And you can see there's not a lot of difference in some cases. In other cases, there is a lot of difference. It's hard to say that these stress parameters come from say a log normal distribution, but they're certainly scattered. And there's no obvious say magnitude dependence in what we're deriving right here. So I think we have to live with just a lot of scatter in these things and a lot of uncertainty. And that's all I have.
Okay, thank you to all the presenters. That's where Norm will come in. He's much more competent than I am to summarize these issues in a consistent way. So he's going to come over with the summary of the different positions, or the overview of what we just went over. So, you want to? No. What about Gail? Is she okay?
There's one comment there.
Oh yeah, but Norm will address it.
Yeah.
You took that in his slide, so that's fine.
But I think it's fine to show that as well. I think that's one thing to start with, and then we'll come back.
Okay. Okay. So
Just put it's on. I have it. We have the essence of it on there.
Okay.
I think you made it so big on yours. I thought it was a slide.
No.
That one, whatever it is. Yeah. And then all the way to towards the bottom. Try that. Yeah, try that. Okay. That's all right. We've got it. Okay. There's a couple items we need to think about on what we just heard, and I think what Dave said and Gail said, and it has been an issue of how we're going to deal with all the correlations. And I think the essence is stress drop is a number that goes with a particular simulation model and a particular geometrical spreading and whatever other parameters you have, such that you reproduce the observed ground motion. So it turns into a coefficient in a model as opposed to something physical. With that, so the key, so one recommendation Gail gave us, combine source and path into a single group. Our groups right now, just so you know, we have a simulation group whose main charge is to crank out the simulations and get them done, or at least oversee that part. So what we would be expanding here really is the path group or essence, when they're looking at this, look at the stress drop at the same time, and that these things are all related. So that's, I think, straightforward for us. So what we will need to do then is, with the available data, go back and estimate suites of stress drops for every method that we want to use and every set of geometrical spreading we want to use. So if we're going to have a point source model, or single corner and a double corner point source model, and I want to have 2 or 3 geometrical spreading, we're going to get a large suite, but each of those then has to go get or be evaluated to pull out the distribution of stress drop that goes with that, okay? So one thing we'll need to talk about, start to head to, is how many cases really are we going to be trying to look at without overwhelming ourselves yet not missing something critical. Gail talked about as well 2 approaches of either the high frequency level or based on calibration of a, let's just say, the point source or stress drop coefficient that goes into a ground motion simulation method. Most of what we've been planning and laying out is really the latter approach. That is, the stress drops that go with the simulation model. I think if Gail and Dave are here, maybe I would take the high frequency level. Is that just considered another simulation method? Is that a way to think of that, Dave? When Gail does her wants to get at quote, more absolute levels of what stress drop are, I guess. I'm not sure how we should be moving forward with that part.
What's the question?
We have 2 approaches that Gail talked about of stress drop. One is the parameters that fit with our model.
Okay.
Okay? And so if I say I'm going to run a single corner model and I'm going to have a 1.2 slope and whatever the Q model is, I can derive a stress drop that goes with that, right, from past earthquakes or a median stress drop. Then I would get a different one for a different set of models or assumed values. But then there was also the approach where Gail said just go straight to the high frequency level. And that's not, as I see it, getting the parameters that we stick into the models that we're talking about.
I guess I didn't understand the difference between the 2.
And Gail, are you still there?
Can you unmute her and I'll see?
She did send me, by the way, her stuff, and I don't know what the hell it is.
Gail, are you there?
Yes.
Okay. Do you want to respond to this? I'll put you next to the microphone. Here, okay. Hold on. Come with me. Okay, you're on loudspeaker now.
All right. Hear me now?
Yeah.
Okay, good. That'll be easier. I was madly typing into the chat box. Yeah, where that fits in is it's interesting to compare that stress drop level from the Brune model to the sort of the corresponding calibration value that Norm mentions that's part of the ground motion prediction model, just as a way of sort of understanding what each one of them means. If we're using a simple point source model, we might expect that we should be able to put in the Brune stress drop value from the high frequency level, and if it's close enough to a point source and all that is done all right, that we should be able to then predict the ground motion model, provided that we have the duration right. So where that high frequency of the Fourier amplitude level really comes in is in basically closing the loop between the Brune model that was sort of the original starting place of the whole idea of doing the stochastic model for high frequencies, and the actual ground motion parameters that you get out of it. I think you can close the loop with a stochastic point source model, but possibly not with a finite fault model.
Okay.
Yes.
It doesn't help me, but okay.
If I try to say how I think this helps us is because while in the simulations that we're planning to run, it's the lower, the second one there, but this is another way to just get consistency checks all at the end. Is that a fair way to say it, Gail? To just see that it all makes sense and fits together?
Yes.
But that wouldn't be the what we'd be using for the simulations. And Bob Youngs is muttering only for the point source. Is that?
No, it's
who said that? Oh,
Ken.
I'm sorry. Okay?
Yes, I think
Is that
that's
right?
fair.
A fair summary?
Yes.
Okay. What are we going to do? And the other was use the MMI data as it is information on large past earthquakes to the extent that we can. So I think this is back to using it as a check as opposed to a calibration. You know, that these data are not inconsistent with our model, that type of a check. I don't know what other checks or experience you have in terms of trying to calibrate these things.
Yeah, I think that's fair. It can be used as a check.
Okay, she said yes.
Yeah. Okay.
Fair.
Oops, I lost something here.
Yeah, you have a few more.
Okay, well, I'm missing something on magnitude dependence. So let's talk a bit about that. So there's two pieces of information we were just given. One from Bob Dara, that in inverting the point source model to the NGA model to try to reproduce that features of the scaling, he sees a magnitude dependent stress drop. The stress drop's coming down with magnitude. Okay, what Anne-Marie just showed us, she gets in apparent stress no magnitude dependence to the stress drop. Are these things the same thing? Are these consistent or not? And I'm reading the note from Gail here, so that the magnitude dependence, let's see, that part of this could be due to the way that we calculate stress drops, and that apparent stress drops are not the same as stochastic point source inverted stress drops. But are their magnitude dependences different? And are their variabilities different? Can we take standard deviations even from what we see in the range from apparent stress to what the point source numbers are? So either Greg or Anne-Marie, do you have a feel of what your numbers, how they relate to point source stochastic stress drops? Are you guys back there?
Yeah, they're thinking right now. They're probably.
Okay.
I see the gears.
Did I open the wrong file?
I don't know, because where are your other files?
I don't know. There's a bunch of...
Let me just go look. Oh, you have an empty one, that's why. but there, no?
Oh, there
there
was,
you go.
okay.
Okay, now we're
That's
talking.
yeah. Come on up, Greg, if you're ready for it. Why do you stay in the background?
Okay, so I've not done the whatever the other one is, the stochastic stuff. But my understanding is, from a quick conversation with Bob, is that you actually are solving for path effects as part of that process. Is that, or at least they're in the problem?
They're in it.
We have a very simple path. So we're looking
Come on up so that
has to come up here.
we can
Sure.
do that or something.
Huh? Leave it there when I think I think
To use an early analogy, they're kind of like two types of apples. We're looking at recorded strong motion data at a site, and we model with a very simple path term and kappa for the site. The Stanford group is taking out the source. They're trying to look back what is actually happening at the source of the earthquake. And their results show that at the source, there's no scaling. I mean, the source, the scaling is the same from very small magnitudes up to 7.2s or 7.3s. And they've seen that in seismology for a long time. To do the analysis on our data, we'd have to pull out all the path terms to take our earthquakes back to the source. Our inversions are what you see on the ground, on your site. So it includes all that other stuff. And we also only, I think you only have one magnitude 7 hectomine, right? It's the biggest one you got? 7.1, 7.2?
It is. There's also the one in, sorry, the northern one in Japan, the Iwate Miyagi, something or other.
6.8, 6.9.
Oh, maybe it isn't 7. Yeah, I'm not even sure.
I think. Yeah, it's somewhere. So we don't actually, if you look at, on our slide, there's kind of a wall at 7. So the stuff really above 7 shows a drop-off. And, there's only one data point. So we're not really there's also that. We're not really sure with the scaling what happens above 7. And we're also only looking at coastal earthquakes in California, where you have, Japanese data set and also some deep earthquakes and one in Wells, Nevada. But I have no problem with the seismological, and that's very well established, is from very small magnitudes to 7s. It doesn't, stress drop between 1 and 100 bars, scales very nicely, linearly. We're concerned more about what's happening at large stress, larger magnitudes, which are unfortunately underrepresented. And I don't want to start wishing for earthquakes.
Yeah, let me just chime in. There are, so I agree with what Bob said. There are some larger magnitude earthquakes, I think, in the Ullman and Shear data. So one of Anne-Marie's histograms for the global data set has about 60-something intraplate earthquakes within it. And I think there are some magnitude 7 plus events in it. I'm not sure how many, though.
So I guess the key is that, again, now we're not comparing apples to apples anymore, since one is really focusing on the source, the other one includes the other effects. And how do we get to resolve that? And if it's just an apparent conclusion, because you look at different things.
How are we going to get at the issue of magnitude dependence of stress drop? Because we need that in our models. Either it's magnitude independent or there's a magnitude dependence, but something has to be decided when we start to move forward what to use. So the question comes back, what kind of data can we get? We're not going to have big magnitude events in the east in which to look at this. Okay, if we say for example, the type of analysis that Anne-Marie just showed is not relevant to these, then we can't use their evaluation. Or the stress drop, the magnitude dependence that Bob just showed was for east or for basically California-style earthquakes, and can that be picked up and moved? What information can we look at to try to get at this? Ken, you have to come up here.
Well, first of all, can you bring up the plots that you were referring to there?
Which one?
Anne-Marie's plots?
Yes, sir.
Comparing.
So just so you know, on the schedule.
Quick observation.
Yeah, okay.
And, yeah, then we'll answer more discussion.
Right afterwards.
So,
Yeah. That's
kind of
fine.
start. Which one? This is kind of rolled all into this mishmash.
Because you can't
Yeah, I know.
separate it.
I know.
It's the plots showing the stress against moment, right?
The distribution or? Oh, there's a
Well, actually,
general, more
it was
general.
the other one, yeah. It was the ones
Keep
that are
going.
more horizontal.
Horizontal, up, up.
And maybe I was misinterpreting those plots.
Oh, that's how, yeah.
The bonus slide, keep going back. That's like there.
Oh, well, these are ones that I saw.
That's
You
not
want the
what
one with the
Air
stripes
bars?
of the,
Yeah.
yeah, okay, yeah.
Those or these guys?
Just more, a few more colors. More,
Didn't
there,
remember seeing
that's
it.
what you want, right? No?
No.
Oh,
You like this one?
The minute.
why don't you
That's
flip
not the
through
one
and
either.
tell us, what does it look like?
There's a,
I thought it was against moment. It was like that, except it looked like there were clusters of earthquakes.
Oh, yeah, it's the beginning, right? That's the previous one, no? Sorry.
that one, there's clusters.
Yeah, that's clusters.
Okay, we'll come back to this
Maybe
one.
maybe it was Greg's plot. I'm sorry. Did Greg show? No.
No, this is
Which
Anne-Marie.
one, sorry, I was chatting.
He's looking for a certain plot and he's not sure what it is.
Sorry, I wasn't listening. Exactly.
You want moment again?
Not this one.
No, it was like, there were like clusters, you know, it looked like analyses of clusters of events. And then the clusters marched along. But it looked like a trend. It looked like there was a moment trend in each cluster, but the clusters themselves looked to be centered about zero. And I don't know, again, I was trying to understand that slide.
Sure. This one.
Yeah, right, exactly. So tell me, there look to be trends inside of that, and my question is, what are we looking at here? Yeah, like for example,
So this is the top plot's from Ide and Baroza, 2001, and they actually compiled a bunch of other studies and made corrections in some for limited bandwidth. But we said before that in order to measure the radiated energy, you really need to be going, as high as you can in frequency. And so if you stop at the corner frequency, you're missing a lot of energy. Yeah, well, this is your paper.
So we noticed this too. So this is, our compilation, but it's based on a compilation done previously by Magar or somebody like that. And there are trends for within the sequences, but not between the sequence. And you may notice there's some hollow symbols and filled symbols. The hollow symbols represent the original estimates. The filled symbols are given the limited bandwidth of the data where the Broom model would put those energy estimates. So for some of those smaller ones, the correction is larger than the measurement. Basically, those earlier studies didn't have the bandwidth to even measure energy. And then the place where the triangle is, that's a selection bias. So for the smaller magnitude events within those studies, or that study, they preferentially got rid of the small high stress drop events just because the corner frequencies were so high. So that introduced a trend that was artificial. If there's more questions, you can go into.
so if you eliminate the bandwidth issues, then
Then you get the solid dot.
much more.
So what Ken is saying, if you eliminate the bandwidth issue, you take away those empty symbols, which is an apparent trend that once you take only yeah, exactly. Just repeating for the crowd. Huh? Gail?
Oh. Hi, Gail.
Gail, you can talk now. You there? Is she unmuted?
Yes, I'm here.
Oh, okay. Go ahead.
That was my comment, though, was I'm a little bit behind schedule because my comment regarded Norm's earlier question a minute ago about the magnitude dependence in the Western stress drop values. So maybe I should hold until this discussion is finished.
No, we're happy and back to that. Yes.
Okay. Well, if Norm wants me to answer that question, my opinion is that I think that most of the magnitude dependence that you see in the stress drop values in the Western North America will come at least in part from the way finite fault distance measures are used in the NGA equations. And I suspect that if one used an equivalent point source measure instead, that a lot of that magnitude dependence might go away. I think that it is unlikely that we could count on a decreasing stress drop with magnitude in the east, except within the context of a model. So again, it comes back to the model context. But if you were just using a stochastic point source model, I think if you got the distance metric correct to be some sort of an equivalent point source measure, then there would be no need for a magnitude-dependent stress drop.
Okay, but Gail, in response to that, and Bob can correct me, they used an equivalent point source distance in in developing the stress drops for the point source model that mimics the NGA magnitude scaling. Is that correct, Bob? He's shaking his head yes. So I think they did that. I'm not sure I understand what your comment is.
Yeah.
They used RJB, but with a magnitude-dependent fictitious depth.
So they did use a magnitude fictitious depth, and did they play around with the magnitude fictitious depth to see if they could make the stress? But I guess what I'm getting at is I suspect that one could make the dependence go away.
Okay.
And so I guess my question for Bob would be, did they try and make it go away? Did they see what they would have to do to make it go away and determine whether that was just out of the question?
Okay, Bob is coming.
Not yet. Maybe tomorrow.
So you have not looked at that. Let's try to. Your goal was really to replicate the stress drop. That's how you fix the distance to get to the. Okay.
Yeah, so the short answer is no. Maybe in the future.
Okay. He's
Okay.
working on it.
We're almost. Yeah, you guys can sit for now. Thank you. Yes, Paul.
Norm, you asked the question of how to look at magnitude scaling of stress drop. Another kind of stress drop is the kind of stress drop you get when you know the seismic moment and the rupture area of the fault. And that's the kind of stress drop that I'm familiar with. And when we look at that, we typically find that in tectonically active regions like Western North America, rupture areas are about twice what they are for the equivalent moment magnitude in the east. So it seems that what you might call a static stress drop from rupture area is constant stress drop scaling, A, and B, the stress drop is higher in the east than it is in the west. Now I realize that this kind of stress drop doesn't have a clear relationship with the stress drop that your session is talking about, but coincidentally, it does turn out that the static stress drops are, I believe, constant stress drop scaling in the west and the east, and they're lower in the west than they are in the east. So that sort of matches how I think the stress parameter type stress drop works as well.
All right. Back to our, so we've got a couple questions for us to answer in terms of what needs we have. sets of how many cases are we looking at for getting stress drops estimated from Eastern U.S. data? Is this going to be, so we're going to have to give a charge to a group to say, looking at the data, how many, what sort of range of geometrical spreading, let me just call it NQ combinations that we want to be using? Is it 3 or something on that order? And then for each of those, you need to then take whatever method we're using and back out the best estimates of the stress drops. Right, so these are point source stochastic model stress parameters. Paul. Okay. We're a cozy group today.
Now, I haven't done a lot of these, i.e. any of these studies, and this may not be the best way to attack the problem, but one way to attack the problem, which might be really useful for forward and inversion problems with small numbers of parameters, like the stochastic stress model, is through a simulated annealing inversion, in which case you generate millions of models, tens of thousands of which fit the data, and explore the parameter space, and you can look at the correlation between the various parameters that trade off. And that way, it might be a very effective way of looking and finding all of these correlations. And particularly, if you choose your cost function cleverly, you could ask to make certain parameters extremal. So I think that might be one way to approach this problem in a systematic way.
Okay. We would set up a penalty function or cost function where we can force one parameter to its extreme and then estimate the others and so forth and get a suite out that way.
See the range of others that were consistent.
That would.
Yeah.
Okay.
Ken, we talked briefly about that. Is that what you had in mind when we talked about modeling? Do you remember? Yeah? Ken, you? Yeah, there's only one Ken? No? Okay. Well, that's what I understood. We talked about it yesterday. About modeling. Okay, the dinner was too good. The beer was great. Okay. What else?
I think that's it. And on magnitude dependence right now, I haven't heard a great thought of a way forward yet. Okay, so part of it is, I think, perhaps making sure we understand any relations between the apparent stress values that we're getting, where we have sort of bigger regional sets to use. But I'm not sure, I haven't gotten something that I could write down and say, here's a clear task that we're going to ask somebody to do to get at this topic. Any ideas, Bob? No? So, yes, Paul. And Gail, if you're there again, we were just talking about the magnitude dependence. So one estimate you said is really, if I repeat what Gail said just before you get started, for the inversion of the NGA models to say, can we force magnitude independent stress drop and adjust something else like the magnitude dependent depth and get the equivalent fit, right? So that's one approach to see if we can sort of show that it's ambiguous to how you're going to model the other terms, right?
Yes.
Okay, well, there are two problems, and you actually just sort of touched on my comment. First, we have to make sure that the magnitude dependence is in the Western U.S. data, because Bob said he would go and look and see if he could find a model that doesn't have it. And that kind of thing could be approached again through simulated annealing inversions. As far as finding a magnitude dependence and then trying to figure out what to do in the East, I have no answer.
All right. Any other comments? on these two topics. So I think we can set something up that will really say to what are the extent we can, is magnitude dependence required in the Western U.S. data? I think that's really what the question that we're coming back down to.
Yes.
That was a yes from Gail, I think? Yes.
Yes.
Okay. All right. It's 3 o'clock. We're going to take our break. Thank you. We're back at
3:15.
3:15. How about we make it 3:20?
Okay.
Because we need to type a few things up here. Yeah. And then they'll actually be back at 3:30.
No, I don't. Did you scale without
I'm aware of those issues, but when I look at this, it seems to me that, well, we have a lot of issues to deal with. But first, if we think back about earlier today, the regionalization issue, if we go on again and have too many regions, I think we might introduce somewhat of a bias or issues for a given region with a specific Q and geometrical spreading. We're going to set other parameters, and we might kind of reduce our uncertainty because we have constrained two things together in a region. But then if we go across boundaries, we might actually have bigger problems because we have more boundaries, more issues to deal with, and I really don't know how we can deal with boundary crossings if we have many of them. So there's kind of an offset there, I think. And I didn't see there was compelling evidence that we have new data that suggests we should change the regionalization and go in smaller blocks. So I think we have to deal with that. Now, Norm is going to come back and focus in a little bit more details on specific issues, but even as we move forward, there were many different, well, a few different approaches to try to constrain some of those issues, but we'll still need to think ahead of what a process is. So there's the magnitude dependence on stress drop. Do we just make a decision, and then we think that normally all those parameters that, to me, serve somewhat of the same purpose, I mean in a broad scheme, the geometrical spreading, the Q, all those things together, will eventually physically come together and fit the data if you set one of those. So these are issues I think we need to think about, whether there's magnitude dependence or not of stress drop, and whether if you fix that, if the other parameters will come into play to make your model work. We just have to make some of those decisions, I think, and be aware of those decisions and document them properly in case that if we have more earthquakes to give us more knowledge, then we can adjust those assumptions in the future. But that's just kind of a somewhat outsider point of view here.
Let me follow on what you just said, and so the art of making ground motion models, all right, is not to find the best data, the best model that fits a set of statistical observations, but we're trying to take a model that is consistent with the observations and extrapolates to where we care about in a, I'll say here, proper way. What's proper is the whole art of this whole thing. So while we may be able to find a huge range of models that are going to be consistent with our observations, we can't simply take all those and let them zoom back to 5 kilometers from a magnitude 6.5 earthquake, or things that are actually going to impact our hazard runs. Right? So that's going to be something that we have to keep track of in all of this, and that gets us back to what can we use from other sources of simulations or other regions in terms of how data extrapolate. But this isn't for us to talk about today, but this has to be in the back of our minds as when we go to start to build the models, they have to extrapolate properly to the cases that matter to hazard. Okay? And that's somewhat what Christine was saying about. We don't want to mess up the problem trying to get fine regionalization that actually makes something else work worse in terms of what we really care about. Let me then go back to, so this is a bit of just a repeat, because I think some of the things that were coming up, a few of you talked to me at the break, are actually being covered. But what I want to get back is as we leave here today, a set of at least, in the SHAC terminology, we call these data requests. And it will go back to the project management to see what we can afford and what we can get done. But I think most of the things we've talked about here will have to be dealt with. So while we somewhat just poo-pooed regionalization for you, the first topic really is we need to update what was done in EPRI, okay, with a stronger regionalization or updated with current knowledge that makes sense. Get new region boundaries, new velocity structures, and then really do the simulations to say what matters. Okay? We don't want to miss what matters. If there's a really strong difference in regionalization, we need to pick that up. Okay, so again, I would point back to Monday when John Adams was talking about the offshore earthquakes propagating as a completely different wave propagation. Well, then we need that because that actually matters. Okay, so we have to capture things that matter. And then we'll go through, as part of this, we talked about inventory, again, of the earthquakes that have been modeled. If ones haven't been modeled that are important, especially in different regions, we need to get some of that modeling done to understand what's there. We're going to really have here the evaluation of the vertical and horizontal, I think, is a key feature that we haven't spent as much time on in the past. Most of the old data were verticals. A lot of interpretations have been made on only vertical. Now we have the luxury of having a lot more horizontal data, and whether or not that impacts us in terms of what we assume or infer is happening in close is really going to be key. So I think we're going to have a task that really looks at that and evaluates what we can use on verticals and to what extent we should be relying on the vertical data. And as noted below, we'll be considering not just simulations but also data and looking at our attenuation or our regionalization. And finally, on the bottom, as we talked about, a requirement is a set of rules, so we don't hand this stuff to the poor people doing the hazard with no way of knowing how to implement things as if we have more than one region. My expectation is we will have more than one region. It's very difficult to lump the Gulf Coast and the rest of the country together, and it may be, that's what we heard, the offshore, maybe it's simply a very different region as well, but that's all to be decided, okay? All right. The data compilation, and part of what I wanted to emphasize here is we had a large discussion of stress drop this afternoon and its correlation with what we've assumed for the geometrical spreading. We did talk about this morning using synthetics to get basically Green's function-based simulations to see if those also provide some constraints to the geometrical spreading. We don't want to be creating geometrical spreading terms in the point source stochastic model that don't make sense or can't be generated in some physical way. So everything ought to fit together. The data compilation, I guess at this point for TAFs, we do have, Gail has done her part, and we're looking for a similar data set for the central U.S., basically summarizing all of the recent data from Herman, and so that will provide for us a composite set which will be our central database for doing this. I don't know an issue of what we need from Bob. We talked about a little bit yesterday, but I think it will be mainly what is currently available and feasible. Is Bob still here? Yeah. No, he's gone. So that will be primarily, I think instead of telling we want every earthquake over this magnitude and so forth, it's really going to be the data that are readily available and are in a format that can be used on this topic. We didn't, there's a mention of ambient noise data, and there wasn't much discussion about that. Does anyone else have a thought about the ambient noise method? I think this is, Greg had talked about the value of these kinds of data. Is Greg still here? Yes, and I didn't come up here, and I'd like to, if anyone has a more detailed question to ask you, if this is something, what would we do with this information, right? If we got it, how are we going to use it to constrain? I think you're talking about Q models. Is that correct? That fit with our geometrical spreading and all of the other parameters. So,
yeah, I just mentioned maybe to prompt you that there is a paper, I think it's in Press and JGR, that has a regionalized Q model at slightly longer periods than 4 seconds. I think it's 6 or 8 seconds for the western U.S. It's parameterized not in terms of Q, but in terms of attenuation parameter alpha, but it's straightforward. with some work to convert that into a Q model. So this might, depending on how it works out for the central and eastern U.S., this might provide a rational basis for performing a regionalization because with U.S. array you'll get fairly uniform coverage.
Paul, I pick on you. Do you have any comments, or Dave, on this approach?
I guess. Oh.
Sorry. Yeah. Why don't you both come on up here?
I don't have my shoes.
Neither do I. My feet are in bad shape.
I can take mine off.
Yeah. Step on our toes.
I guess the only concern I have is whether the phases are appropriate. I mean, when we're analyzing strong motion data or data out at regional distances, we're generally talking about LG phase. And with the noise, if it's not really the same phase, then the Q that's attached to that may be different. That's my only concern.
Well, I think if nothing, well, first, do you know of any studies using ambient noise for structure or Q in the central or eastern U.S.?
No, but that doesn't mean there aren't any.
Yeah, I think the first thing we should do is at least survey the literature and the recent work to see what's out there, because the stuff they're doing with this ambient noise is really interesting, and it, there may be something interesting out there, or there might be something that leads us to suspect we could get a new useful result. So at the minimum, we should do a literature search and talk to our colleagues to find out what's happening.
Let me put that in, and then we'll do the start. Did you type it in already?
No.
Oh, God.
Do you prefer? I can type it on your version here.
Why don't you do that, and then we'll have it somewhere, okay? And then we'll try to. Yes, you are excused. Thank you. Now what am I trying to click? All right, and then we had talked about a lot this afternoon, again, finding stress drops and geometrical spreading and Q all and model simulation method as packets, right, and finding the suites of those that are going to be available. The suggestion then was to use annealing algorithms. Is it? Simulated annealing methods, and I think Frank had mentioned that they've got some of this working already for point source models that has been done on applied to some of the work in the Pegasus project that can be used to crank out a lot, as you said, huge numbers of models that are consistent with the data, and from those we can start to pull out those which we consider applicable or as I said, would extrapolate in a proper way. Okay? Any other comments on that approach? Did you write that in there, simulated annealing methods? Because I would never be able to spell it.
I'm not sure either.
Spelling is not my strength at all.
And enjoy it.
Thank you.
Okay.
So, I mean, the basic thing is that we have committed that here all this will be done in a correlated way such that we get sets that fit together and can be then applied together properly as we move forward. This is the same type of thing. Whatever we do, whatever sets we do, all the validations that we do will be done for whatever combinations we get. So the validations will lead to different stress drops, and the evaluations of the methods will sort of follow from that. This is this.
Gail wants to comment.
I'm sorry.
Do you mind?
No, of course not.
If you just pick her up and put her next to
Here you are, Gail.
Hi, I'm back again. Again, commenting just on correlations, just a couple of slides back, as well as the stress drops being different for the different attenuation models. One thing which perhaps I didn't stress very much in the previous comments is that one should also consider what magnitude value works. Obviously, the stress drop affects the high frequencies, but Dave showed in his slides the trade-off of how the stress drop you need varies quite a bit depending on the moment magnitude that you assume for the event. And for most of the events, we don't actually know the moment magnitude. Certainly for the few largest or the recent bigger ones, we do know what the moment magnitude is. And in that sense, if we know the magnitude, we can, in some ways use it as a constraint on what the geometric spreading has to be, at least in close, because there's no point predicting a stress drop that would predict a moment magnitude that is totally inconsistent with the known moment. So, for example, we know that, my 2004 model, we now know that you can't take that 1.3 all the way into the source because somewhere between 10 kilometers and 1 kilometer you have to flatten it out. Otherwise, you would be over-predicting the moment for all of the events. So the moment also comes into it. And another thing to possibly look at is for each event is essentially what combinations of moment and stress drop and attenuation will work with the data. So I just wanted to make that comment that as well as looking at how this stress drop interacts with the attenuation, that we don't want to forget the moment magnitude as well.
Oh, closer? Sorry. I didn't have you close enough, but I heard what you said. The question that we will face on this scale is we have moment magnitudes established for these events in the source characterization group, and changing those is a big problem for us.
Yep. That's okay, because if for events that you have a moment established, then what you would need to do is to essentially use an adjustment factor on what's happening in close to the source, so that if you're looking at a stress drop, say, in the context of a Bruin model, you have to use, you would need to adjust the near source attenuation from whatever the distance range is that is constrained by the data, which is at best 10 kilometers, as you go into the source, so that you get the same moment magnitude. That was one thing that we found in the study that Dave showed some results from earlier, the Boer et al. 2010, is that if you use the Atkinson 2004 model, you would predict really, really high stress drops if you assume the moment magnitudes that we know are the correct moments, but you would also end up with a mismatch in the moment, and that if you take the long period end of the spectrum, you can't match that moment if you take the 1.3 rate all the way back to the source. So you essentially need to make an adjustment factor so that you match the moment, right? So there's no point matching the stress drop, is what I'm saying, if you're not also matching the moment. So if you need to lower the spectrum to match the moment, that also affects the stress drop.
Right. So then you can so you're talking about adding essentially a constant or something that can be brought along with the event that deviates from the moment?
Yes. Yes.
I have a yes from Gail and a no from Dave. So that's Come on up. Sorry.
Well, it wasn't like a scale factor that Gail, if I understand it correctly, it was changed the geometrical spreading factor so that in close, like 1 kilometer, she got the proper moment. Okay,
yeah.
So I don't want to give you the impression of something that's independent of distance.
Right. Well, that's true, but I guess the reason I was nodding my head for a scaling factor is it has the same effect as a scaling factor. So, for example, a trick that we found generally worked to match the moment was if you assumed that R to the minus 1.3 applied into about 10 kilometers or to the epicenter, but then you had a r to the minus 1 from the hypocenter to the epicenter, say. And if you look at the difference between, in the first 10 kilometers between r to the minus 1 and r to the minus 1.3, that's a factor of 0.3 log units, which you could think of as a scaling factor of 2.
Okay. Okay. All right. Thanks, Gail. Sorry. The magnitude dependence that we talked about, so as far as I understood, the decision or the recommendation was to see if we can, the magnitude dependence that's implied by the NGA models, is it required by those models, right? So, and did I put this? This is a different slide. Here we go. So we would evaluate if this magnitude dependence is required. Can other terms, so having, say, for example, what Bob Dara showed, can they pick up the same effect through a magnitude-dependent fictitious depth or whatever other parameters we're allowing in the magnitude scaling? The other question we'll get to later is variability of stress drops. So our focus right now has been on central values, medians, and whether variability is going to be transportable. You know, can we take this from the west back to the east? Do we need separate ones for the east? Can we use variability even from the, let's say, the apparent stress? Does that variability have anything to do with the variability of the stochastic values? Part of this will really be related to the standard deviation, the sigma group, right? Because that's what's going to become standard deviations of the event terms. But I think we need to be thinking about how we're going to get these variability terms in later on, because right now I think it's not established. Other than we have a number from the west, right? Was it point? Do you remember what that number is, Bob? Is it 0.4 or natural log units?
The variability is like
0.5. So
from the simulation.
the variability of your stress drop that you get from your validation. 0.5. Okay, so that's the kind of number that without any other information we would sort of be starting from, but it would be good to have anything else that would help us constrain what that is, because that's going to be a significant player in our total standard deviation of the ground motion model. But I'll leave that as just to note that's part of sigma task. We're not going to talk about that in detail tomorrow, but that'll be something to follow up on. And I think that's it. So anything else that you see as a data need for input into the point source runs in particular?
A data need.
Yeah, things that we want to say, we want to have somebody go do for us because we think we are missing information.
Duration versus distance.
I was typing that when somebody interrupted me, is what I'll say. Yeah, so I don't, they could, I don't know. So can you add that in there? And a deriving model for duration versus distance using the new data set.
Okay, where do you want me to add that?
I think it's...
yeah, you have it in there. Derive a new distance dependent on duration model.
Yes.
It's there. You have it.
Okay, I do have it. I was trying to get it in there. So this is, Dave, this is what you're after here?
Yeah.
Okay. Any other tasks? Ken? Come up here, please.
Well, you can focal mechanism. I didn't see that. We had discussed that.
Focal
You
mechanism.
mentioned difference between horizontal and vertical as far as geometric attenuation, maybe focal mechanism.
Or the geometric.
The geometrical spreading from different mechanisms. Okay. Can we put that on there?
Yes.
Any other? So that would be a simulation approach as opposed to a data approach, right? So that would be...
Well, human data may have
Exactly. It could be a data issue.
So I think what Gabe said is there's maybe enough data to actually resolve this between
Shed some light, at least.
to shed some light on the mechanism dependence of the attenuation.
That's in your data.
And no, it's the one Paul Herman will put together.
Okay.
That's the combined set that we're going to be looking at, Bob's set and Gail's set. And the one that Chris Kramer and Gabe. So all that's going to be pulled together into one big data set to look at. Other tasks. Paul?
I had a couple of thoughts.
Huh?
One is, does it make any sense? Is there any value in doing, well, Walt and Bob Dara have done the inversion of the NGA GMPs. Will anything be gained by inverting the data directly as opposed to inverting the GMPs? Will that shed any light? That's one thought about that. The other is the only constraint we have about the large events in the east is macroseismic, again, intensity and paleoliquefaction and so on. Does that help us at all, or does it simply provide a kind of a sanity check? Because that's more questions than tasks at this stage.
What we talked about earlier was a consistency check, that the models are not inconsistent with the scaling derived from that, as opposed to deriving them directly. But do you have something on that, Paul?
I think the problem with using the paleoliquefaction data is the magnitude, because the magnitudes of most of those events are derived based on estimating liquefaction and ground motion models. So the magnitudes are circular in the sense that they've been calibrated to specific ground motion models that exist, and estimating the ground motions those models would produce, and then evaluating whether the sites would have liquefied or not. So, you know, size estimates, for instance, the size estimates now that we're using in the current source characterization for New Madrid range from 7 to 7.8. So what's the size of New Madrid?
Okay. But I think that still, whatever observations we have, we need to make sure we're not creating models that are inconsistent with those. And I think the biggest issue may be if the models we come out with are significantly different from those that were used by the source characterization group to bring back the magnitudes, then we've got this whole iteration problem to deal with.
I'm not sure I got your last comment. Can you repeat that? No. I wanted to bring up with the...
Speak into the microphone.
Okay, so Adrian Rodriguez Marek, is that? Okay, so he sent us an email suggesting that what we could do instead of just looking at magnitude themselves is that once we have our GMP models, we have liquefaction sites, and then go and see if we can get those magnitude backs based on sites that liquefied, so then that would avoid some of the circular reference. But again, just as a check. Regarding what Gabe mentioned, if there was any potential value in looking at the data instead of the GMPs for his inversion models, Gail, I don't know if she wanted to talk, but she said that yes, there would be value in there. So can you check, did she want to? Is she unmuted? Do you want to talk, Gail?
Yeah, I don't need to talk. That was just a yes to Gabe's question. I think that's
okay.
That's very important.
Thank you. So yes, she said it's very important.
Oh, okay. So
Adrian is here on the line, and he can probably explain. Oh, can he be? Hold on. Oh, so Adrian, please text what your number is so we can know how to unmute you. We need your phone number.
Virginia.
No? What's your area code? 540. Is there?
540.
Okay.
Thank you.
Okay, so let me talk privately. Hey, Adrian, you there?
Yeah, I'm here.
Okay, can you please use the handhold instead of the speakerphone, and I'll put you on a microphone so you can talk to the room. Are you okay with that?
Okay, yeah. Can you hear me?
Okay, thank you. Okay, go ahead.
What Paul raised about paleoliquefaction for duration is completely true. You can.
Hold on. You have to speak louder. I'm sorry, we can barely hear you.
Okay, can you hear me now?
Try.
Can you hear me now?
Yes.
You cannot use paleoliquefaction data to constrain duration separately from magnitude. In fact, what we are doing in order to try to get magnitudes back is we are using correlations between magnitude and duration from known data and applying that to the paleoliquefaction region. So in that regard, I think Paul is the one that mentioned that there would be for sure circular thinking. Where you can avoid circular thinking is you can see which proposed ground motion prediction equation gives more stable estimates of magnitude for different paleoliquefaction sites within a region. In that case, you wouldn't be using circular thinking when trying to use the paleoliquefaction data to see which of the prediction equations matches better a set of paleoliquefaction data.
Are you implying that we would be essentially ignoring the current estimate of the magnitude and getting that again separately to find the ground motion model such that it gave the most, as you say, consistent estimate of the magnitude at most paleoliquefaction sites? Is that what you just said?
Yes, David. Yes, that's what I said. I think with paleoliquefaction, you're just adding one more constraint to the data. So one approach is to trust the magnitudes that you have and then see which of the ground motion prediction equations matches better the data. That's one approach. But an alternative approach is to ignore the known magnitude and just see which of the ground motion prediction equations give more stable estimates of magnitude for different sites.
I think that we understand what you just said, and part of it we'll have to talk about with our sponsors is if that is not a priority, is this is an untenable situation of changing stuff that they're just finishing up. But
you would like to feedback?
Well, how can you start to run that? I mean, if you don't pick the model that is best given their estimates of the magnitude, then how can you start to run the hazard with their magnitude-based models, their source characterization? There's some issues we'll have to deal with. Ideally, we want the right thing, but
realistically, we want the product.
I think we'll talk about this not in this workshop format as to what are our limitations. Anything else?
Thank you, Adrian.
Bob, anything in terms of what you think we need to have? Or Martin?
Looking at the horizontal and vertical?
Yes. Yeah, so we have that's a task that we have to understand that scaling and the interpretation of any of the older data. Martin, anything else you can see that we need to have? Paul, anything else? Okay. Anyone else in the room have topics they think we ought to be critical for getting our point source or stochastic models working? And I think, Ralph, what you talked about with me at the break, we're addressing by looking at some of the Green's function-based geometrical spreading to make sure we're not creating a model that is not physically possible. All right? I think we are finished with that part.
Yes. Did you want to revisit some of the theories from this morning?
I already did. I covered this morning. So what you've seen now is I have extra slides.
Yeah?
Yes, I do.
Okay.
Those are my bonus slides. When I want to write out what really happened at the meeting, I get to use those. Okay, so we've gone through the summary. We're now at comments. So PRP, you guys need some We need to dance because they're talking a little bit. Absolutely. You need to come up here.
But just want to make a comment that Art Frankel has done some work 1990 on high-frequency attenuation in New York State and South Africa, where he investigated the geometrical spreading, and he came up with a physical model of why this is deeper than 1. I think this should be just considered as a piece of information.
Okay. No, that's something we need to include. We had hoped to have Art with us today, but that was not available. Other PPRP comments, or you want to save them for us for later?
We have a question.
Please come up here. I didn't hear you. It's slightly off topic, but related.
Is it SHAC?
It's totally SHAC, or shock, maybe. Our feedback today is we like what's happening. We like the fact that correlation is coming in, and there's the idea of bringing these parameters which only have meaning together is great, and the idea of merging source and path we also think is great, and we'll talk more about that after. But our question is and it's genuinely, it's not a position statement, it's a genuine question for us to understand better. In terms of the primary objective as we understand it, which is the delivery of models for horizontal and vertical response spectra on hard rock, can you explain to us, so we to improve our picture, how the work of the geotechnical working group, how it fits into that aspect of the project? We can see that they provide amplification factors for application elsewhere, and possibly other correlations with other relation with the interpretation of the data, but we'd be very grateful if you could give us a picture of how they fit in, how their work fits into the primary objective, which is what we understand as being governed by the SHAC 3 framework. Is that?
Go ahead. Okay. It's a challenge? Okay. So my understanding from all the discussions we had the last few days, there's definitely one place where they're essential is when we're going to go rock to the surface, where the kappa, the estimation of kappa, is going to go from the pure path and then to a site, this site kappa that is rock. And that's my understanding how this is critical for the rock. Norm, do you agree, or you want to expand or disagree?
Let me put it a different way. How's that? I think what we're the key thing we have to do on our data set that has site response in it is get it out, right? Okay, so our observed data. Now, how are we going to do that? Because of the data that are available, some fairly simplified approach is going to have to be used, right? So whether topography-based or whatever, some remote surface geology, whatever sort of a method will have to be used. That's one of the tasks I think we identified the other day that will get someone to do that. I don't see that as the primary topic of the working group, with the geotechnical working group. They are much more focused on the more technical aspects of really site response when you have information and how do you get good site factors out. I believe updating NEHRP factors for the Eastern United States and that sort of effort. So we're going to have to talk as a project, but because we are not treating that, trying to get at center, body, and range, it really has a fundamentally different place in this project. It is a piece of the ground motion problem, but we're not going to have 10 different models of site response that we push through a whole big broad logic tree, which, for those of you that don't know, we have done on the Pegasus project in a explosion of level of effort that is not something you want to get into. But we're going to have to talk about that some more with our sponsors.
Well, I guess I don't know to which extent everybody is on the same page here, but there's an objective for DNRC, which is that rock estimate ground motion, and then ultimately a model
or procedure to get the site response within the hazard then to hopefully be used by USGS and other people as somewhat of a generic site profile or procedure to develop the site response in there. So to what Julian was asking in part of the, just defining that rock ground motion, well, they're going to help in removing the side effects in there, but they're not contributing. But the kappa, they're playing a role there, right?
Yeah.
Okay, so good.
and their key, I mean, the reason for having this all integrated is their site factors have to be consistent with our reference rock.
Yeah.
And if that's not done, everything won't fit together. So it's got to be integrated. I'm not sure we're going to bash them with the same SHAC kind of requirements. But Yusef, do you want to respond?
Yusef, why don't you expand on this? Because if we take the site effects off in some kind of way that's not consistent, then our data is wrong, right?
Of course, as geotech engineers, we like to think of ourselves as very important to the whole process. And this is something I'm sort of learning through the process the last couple of days. If we are defining the product in terms of ground motions at hard rock, a portion of what we're doing falls within the SHAC process. The other part we'll have to decide. I think this is an outcome of the discussions. Reference rock, kappa rock, site effects at recording stations have to be subject to that process. And to the extent that for example, site effects at recording stations will benefit from everything else we're doing on site effects, that will fall within the SHAC process. Because while we're talking initially, we're going to use simple methods. Potentially, a few months down the road, we may use something a bit more advanced based on what we're doing in terms of site effects. Now, in terms of the site factor functions that we're going to develop, that's important for the overall project. I don't know about the relationship for the SHAC process. So it is very important because it's going to hopefully affect a shift in how we're thinking about the ground motion and site factors, which are, as you mentioned, dominated by the current NEHRP. Very, very simplistic, simplified approach to the process and does not take into account the special geology we have in the East. Thank you.
Anything else? Julian, anything else from your group? Or no? Okay. Not for sponsors. Annie or Larry or any?
No. Well, we just talked about site response for DOE, but we can talk offline.
Okay. Public comments. So anybody who's dying to say something, what we're doing, if it's on track, not on track, what did we miss?
All sounds expensive is my only comment.
Nothing? You're all content? All right, let's break here.